Yeah, thank you very much. Thanks for the introduction, and it's really nice to be here. Okay, so today I'm going to talk about how do we make robot manipulation to work. So I'm going to talk about something in the high level. I'll also talk about some of the concrete work we did along this pathway. And yeah, just let me know if you have any question in the middle. Okay, so before actually talking about the actual things, let's look at some cool videos, right? This is a 1-year-old baby looking at the television, and he's able to do a lot of fancy stuff that most of our robots couldn't do nowadays. But I think among all of them is the capability of looking at the TV and immediately doing what the TV is showing to him, which is super impressive. And this is actually not only true for human baby, but it's also true for animals like dogs. Okay, so what this husky is doing is his owner has a crippled leg, and the husky two husky dogs just run everywhere like it. So not only interesting this is, but it's also super impressive that the dog has a capability of understanding what a two-leg crippled walking means in 4 legs setting. So it means that the dog has really profound understanding of the meaning of this behavior. So, I think from this, I think this is a super fundamental capabilities of human beings and those animals. That is, the first principle, I think, is we are able to imitate in a very profound manner. So I'm not saying imitation in a very low level, but imitation in a very high level, meaning I can look at from a third person's view and understand from a third person's view and execute in the first person's view. And we can also transfer the embodiment, for example, from human being, from 2 legs to 4 legs. We are able to do that. And it is also semantic. It's not just trajectory tracking, it's semantic imitation. So besides this profound imitation capabilities, I think another capability that is also very important is called the reinforcement. Okay, so let's take another example. So I think probably all of us have seen the Olympic swimmer, how they swim in the swimming pool. And we probably have seen like hours of it, maybe tens of hours of it. But when we swim by ourselves, this is what we do, right? We can swim, but it is much worse than what Olympic swimmer can do. So this shows a complementary view of the previous imitation part, where if you're only doing imitation, you are not able to achieve this super high success rates that a very skilled performer or skilled swimmer could do. So the second important category of the manipulation or behaving principle, I think, is the you need to have extremely efficient reinforcement learning in the physical world so that you can polish your skills so that it is much better than the initial policy, like when you're initially learning to swim. Okay, and I think what I discussed actually shared a lot of similarities with what we see at the moment with large language models. So this is a typical training pipeline for large language models. And actually, looking at the others is very similar to the pre-training, right? You read a bunch of text on the web, and you understand what the other people says. And for the RL part, it's also true in large language models if you want the model to be able to write some code that is able to execute without giving you a compilation error every time. you need it to be able to practice the, for example, coding or essay writing in practice and give it feedback, letting it do RL. Okay, so going back to manipulation, I think manipulation has to follow similar paradigms as what we see in the human beings and in animals, as well as in the LLMs. So this is what I call the manipulation data pyramid. Okay, so at the bottom part, we want the model to learn from a large quantity of data. For example, human data on the internet of human doing things, or simulations of simulation doing like object avoidance, path planning, learning from large quantity of those data. And this will equip you with the prior knowledge that we need to have when manipulate things. And in the second stage, I think a embodiment-specific fine-tuning is important because you need to have the robot to know what is the physical limitation, like how long I can stretch my arm, like how much the payload my arm can have, etc. And in the final stage, it is a reinforcement learning stage, which polish your skill so that you don't drop your models frequently, and you can insert a very small needle into a small hole very accurately, and that is where, in accordance with what we observe in animals. Okay, so although I think the bigger paradigms is already there, we still have a lot of details that is not yet figured out. For example, for a large-scale pre-training, what kind of data we want to pre-train on, and what kind of losses we want to pre-train on. And for the second stage, what kind of, how much data we need to collect in order to fine-tune the policy such that it can work on this specific embodiment. And for the reinforcement learning part, since we want to do it in the real world, it needs to be very sample efficient. But reinforcement learning is known to be very sample inefficient. So there are a lot of algorithm design that needs to make in order to make this happen. Okay. So in today's talk, I'll talk about some of the work my group did along this so-called data pyramid. And specifically, I'll talk about three works. The first of them being pre-training. Particularly, we want to answer the question of, can we learn motion level of information from human videos? And then I'll talk about how much data we need to collect in order for the robot to be able to adapt to any environment. And lastly, I'll briefly talk about how to make reinforcement learning sample efficient enough so that it can work in the physical world. Okay, first part, the pre-training part. What should we learn to pre-train our models so that it can hopefully do everything in the future? Actually, there are already a lot of great works doing the policy pre-training. For example, this is a work called Pi 0.5 from Physical Intelligence, which use internet scale vision and text data as a source of pre-training information. However, it is still suffer a lot when it is deployed in the real world. So what's missing? I think it is a motion level of information that is missing because if you look at the internet scale text and image data, it is mostly static, right? It doesn't give you the detailed information of how do I pick up this bottle? How do I pour it into another cup? It doesn't have that. So those kind of motion level of information is only available in the robot teleoperation data, which is scarce and doesn't constitute the large portion of the pre-training data. So a very straightforward idea is that how about let's reuse the huge number of human video data on the internet, and because they contain a lot of those motion level of information, And hopefully we can complement the existing model with those motion level of information. But the central question is, are we really able to learn motion level of information that is useful for the robot? Because the robot doesn't have the exact same hand as human, and the visual appearance is also very different. For example, if you are using a Frankel arm or Unitree G1 robots, the visual appearance of those robots is also very different from our human beings. So the first work I'm going to talk about is about can we actually transfer the motion information within the human video data to the robot. So more specifically, this is experimental design that we designed. So during the training time, we have two types of data. Okay, so this is have data. We have the robot data for some training tasks, and we have human video data for some eval tasks. And during the evaluation time, we won't eval any of the tasks that we have robot data. We'll only be evaluating on the tasks that only have human data. So, as you can imagine, if during the eval time, we could get some non-trivial, non-zero success rates out of those eval tasks, then it means that we could somehow transfer some of the knowledge we have learned in the human data to the robot data. So so more specifically, this is some of the more concrete visuals of what we do. On the left-hand side, this is a human wearing a VR device, capturing video all the time, while the human is doing some of the manipulation things. Although we did restrict the human to be a little bit robotic, as you can see, it's not quite human-like behavior. But that is because our robot has the operation space constraints. It couldn't be as dexterous as a human being at the moment. But I think in the future, if the robot's physical capability is not limited, we can totally relax this robotic behavior. And on the right-hand side, we tally up a bunch of teleoperation demonstration data. And it's worth to know that the two left and right-hand side doesn't have any task that is exactly the same. Because the point being, we want to evolve on the task that we have never seen robot data. Okay, so the method we are using to jointly learn from those two types of data is relatively straightforward. What we do is first we extract the hand poses. So it's a bunch of key points, and we retarget the hand poses to the robot morphology. And on the vision part, we didn't change anything. So we just keep the original image of the human videos. Okay, so then we obtain two data sets. One data set is robot teleoperation data with the robot cameras and the robot dexterous hand future motions. And we also obtain a human data set with human visuals and humans' hand keyframes retargeted to the robot's morphology. And what we did is we just mixed those two types of data to train it in an end-to-end manner. So nothing fancy on the algorithm side. Okay, and then we eval on those 10 tasks that has never been seen in the robot data. For example, using a towel to wipe the table, closing laptop, some pick and place like open the box and put a toy into the box, etc. Okay, so a question for you. So how much is the success rate, do you think, for those tasks has never been seen in the robot data? You can just shout out your guess. 20%. 20%? Okay. 100%. Okay, you are very optimistic, right? Well, anything? 0%. Yeah. But it is 20%. Okay. So, yeah, initially I didn't even expect this to work because the visuals are very different. Okay, let me explain this chart for a little bit. So this chart, we have 2 bars, which is one of them stands for diffusion policy from Shuran's group, and the other is pi 0 from physical intelligence. So DP has no pre-training, but it has pre-training on the vision part. Pi 0 has the pre-training the physical intelligence did. And both of them are trained on the exact same data with human data mixing with robot data. Okay, so those 2 color bars are just 2 different neural network architectures and initializations. But the methodology and data used to fine-tune them are exactly the same. And on the right-hand side of this chart, there are around 10 tasks, which are the tasks that has never been seen in the robot data, but seen in human data. And on the left-hand side, this is the average success rate for both of the methods. Yeah, so you can see that like it has some success rates, but it's pretty low, right? It's 20%. But I'm pretty happy with this because it shows that you can achieve some motion level of transfer from human data to the robot data. And this is great because we use it as a pre-training objective. We don't need it to have 100% of success rates. We just need some information is there. And actually what we did is, yeah.
What is the bread bucket test?
Is picking up bread and putting it into a basket.
Oh, picking up bread and putting it in the basket.
Yeah.
I'm curious where you think that this transfer is coming from. Like, is it coming from, do you think, a stronger visual representation? Or is there something inherently about co-training on the motions of, like, thinking that is helping, like, with this transfer?
Yeah, so the question is how the transfer happens. I think first, both of the methods has a pretty strong vision backbone. And I think that is a prerequisite because otherwise you couldn't even recognize what is a hand, not even to say making some connection between human hand and robot hand. So, but second, I think there is definitely motion information that is learned and transferred between the 2 data sources. Yeah. Yeah.
You found variations under each category as for their roles of the data set. So like for example, like for a close lock or maybe like for different variations, different views where the objects are faced differently or different types of objects.
The views are similar, but the object locations are different. Yeah. Yeah.
I'm curious how well you think this would do if you didn't pre-train on the robot data at all, only the human data. Like, is it almost just replaying the human action and getting some success?
Yeah, we have actually tried that, but we didn't list it here. The question is, what if we don't have robot data, just train on human data? So the issue with that is it has some trend, but it couldn't succeed at all because it just don't know how to grasp anything. Yeah. Okay. Yeah. So actually, 20% is a pretty low number. So, but the number is low doesn't mean that it doesn't learn anything because for a success to be counted as a success, you needed to complete the whole trajectory. You needed to not only pretend to grasp the bolo, but actually grasping the bolo. So we have a second evaluation by using the rubrics. Okay, so basically we define like, okay, moving towards the object give you a few points, and picking up give you another point, and pouring give you another point. So it's a much more detailed evaluation of the behavior of the policy. So so this is exact same method, exact same task, but using different evaluations. And we see that actually, even for the tasks that achieve 0% success, we still learn quite a bit of motion from human data. Okay. So this is, I think this is showing some good signs, but of course, this work is limited in the sense of we as humans to be performing robotic actions. And I think there's still a lot of work to be done about how do we scale this to much in the wild, internet scale human videos, and those are much more challenging. Okay, so that is about the first work. And so in the second work, I want to talk about after, suppose we have some pre-trained policies and their zero-shot performance might be something like 20%. And we need to collect some robot, for example, teleoperations or UMI style robots specific data to fine-tune the policy so that it can achieve a much higher success rate. But the question is, can we actually afford to collect the data to fine-tune the robots? Or to put it in another way, how much data do we need to collect before the policy can work really well in the wild? So the second work I'm going to talk about is called the data scaling law. So basically it's trying to study in imitation learning how much data we need to collect before we can have the robot to work really well in the wild. Okay, so this is my students eating hot pot in the restaurant. And there's a Franca robot pouring tea for the student. And it's worth to note that the Franca robot has never seen any hot pot restaurant, nor it has never seen anything besides they're actually eating the hot pots. So it has never seen this scenario. So it is actually able to do zero-shot manipulation in the wild without ever seeing this. Okay, and of course it can do many other things in many other scenarios. For example, in this setup, the robot is even able to do something in the elevators, which we definitely didn't train on. Okay, so. So it's actually about talking about the data scaling law. It's actually about how do we characterize the amount of data we train on versus the generalization performance. So in order to evaluate how well the robot generalizes, we need to first specify what do we mean by generalization and what is the dimension that we eval on the generalization. So actually, people have done a lot of generalization study before, but most of them are kind of doing generalization eval on color, texture stuff. But I think a more natural way of evaluating the generalization is by environment generalization and object generalization, where environment generalization naturally includes all the things like background, lighting, etc. And object generalization also naturally includes those object textures and different sizes of the object, etc. Okay. So in this work, there are two goals. The first goal I have already talked about is what is the relationship between the data I collected and the performance of the model. And the second goal is more practical, is that given we have known about this, how do we design a data collection schema so that it can work in the wild for any of the new tasks you care about? Okay. So we collected around 40,000 demonstrations and did over 15,000 evaluations. And this is the main takeaway. Okay, so yeah, this figure is a little bit complicated. Let me explain it. So left and right are two tasks, two evaluation tasks. So let's just focus on the left-hand side. And the x-axis is actually describing the diversity of the data we collected. So we measure diversity by measuring how many environment and object pairs we collect the data from. So yeah, if you just use one object and collect data in one environment, that is very limited diversity. And we did up to 32 environment and object pairs. And the y-axis is the normalized score. It's just a Rubik's evaluation of the policy performance ranging from 0 to 1. Okay, and there are also several colors of the lines, where each color denotes how much data we use in each of the environment. So here, in each of the environment, we collect 120 demonstrations. So 100% meaning that we're using all of those demonstrations in each of the environment. And for example, 25% meaning we are using only 30 demonstrations out of those 120 demonstrations in each of the environment. So for example, this 8 here and this orange line here, meaning that we are collecting in 8 environment and object pairs. And for each of the environment, we're using 30 demonstrations. Okay, so there are a few conclusions. So obviously, the more diversity you have and the more data you have, the better the performance. But this is not very interesting. This is totally expected, right? And I think what is the interesting part is that if you look at this point, okay, if you look at you have 32 environments, and the different amount of data actually don't matter that much. If the number of demonstrations reach a certain amount. So actually this is 100% and this is 25% and this is 50%. So actually those three data points actually fluctuates around some number, and they actually are not so different from each other. So it means that if your diversity of data has reached some level, then you actually don't need to collect many data in the.
You're saying that we need 25% of 30,000 unified hours of data to validate your analysis effectively?
So this is 25% out of 100 demos per environment. Okay. However, if you go lower to a lower diversity regime of only 4 environment object pairs, then 25% is not suffice. You will need 50% to be as good as 100%. Yeah, so I think that's a very interesting phenomenon. And you can imagine if I go all the way to infinite number of environment object pairs, you probably just need one demo for each of them, which is totally sensible. Okay. Okay, and a third conclusion is that we can see that the diversity is much more important than the absolute number of demos you collected. Because if you look at the highest dot, for example, for 8 environment object pairs, even for 100% data is still lower than 32 environments with 25% of data. So that is saying if there is a trade-off between allocate your data to more diversity versus more demos per environment, you should allocate that to the diversity part. Okay, so yeah, so that is the generalization performance, and we all know that in large language models there are scaling laws and there are actual curve fitting to this data scaling law. And we actually try the same, okay? So we're on the x-axis is the data, and the y-axis is the model's performance. But here measured by the so-called optimality gap, which is how far away are you from the perfect policy. And the 6 figures are just different tasks and different measurement of the diversity. And we see that almost all of them has reached an R score larger than 0.95. So this means that in imitation learning, we see no difference. They still obey the scaling law pretty well. No difference from the large language models. Okay. Yeah.
You, in the previous equation, you mentioned the quantity of data. Sorry. In the previous slides, you mentioned the 2 axes of data, either diversity or quantity. Is this one strictly just talking about quantity, or is that also mentioning diversity?
So this is only talking about the diversity. Actually, we have an experiment that's trying to fit quantity versus the model's performance, and we see that there is actually a plateau if you limit your diversity to the same amount. Yeah. So a better name might be the diversity scaling law. Yeah.
Is there really it seems like the more diversity, the better, the most difficult. Is there a way that you determine which is the right kind of diversity to show to the models? Because, yeah.
That's a very good question, but we actually didn't study that. So, there are many axes of the diversity. For example, the placement of the objects, and so here the diversity in our case is environment and object diversities. But I feel like if you extrapolate from this conclusion, you just make everything as diverse as possible. That's probably the best. Yeah.
You're saying it's possible to increase the diversity through augmentation or regeneration rather than relying on the overall pattern?
I think it is possible. But there is I feel like there is a no free lunch theorem because when you are doing data augmentations, like we can do, for example, random crops, and that will work. But it's very hard to do. Like, for example, if I want to reach something behind my laptop, I need to circle it around it. So the data augmentation couldn't really do that. So I feel like the data augmentation could be doing some of the low-level things like the lighting, texture, but couldn't really do a lot of the motion level of augmentations. So that's my feeling, because it's very hard to edit the data so that it actually is a different motion. Yeah.
Do you have a sense for how different placements or things need to be to actually count as a new environment? I'm just trying to get a sense of what diversity means here.
So what we did is, so for example, if we collect data on this table, that is one environment. And if I turn around to collect data, that is counted as a different environment. So it's just the majority of the pixels you see is different than we count it as a different environment. It's not necessarily the very far away physical environment. Yeah. Okay. So for the second goal, what we want is if we understand the data scaling law, then can we do a new task to achieve pretty high success rates? And if we can, how much data we need to collect? Okay. So those table on the first 2 tasks, this is a task that we study to establish the data scaling law, and the data collection schema is not optimized for efficiency. But after studying the data scaling law, we kind of came up with a schema that's optimized for diversity, right? So the final schema we are using is find as many environments as possible. So in this case, we find 32 environments. And for each of the environments, collect about 50 demonstrations. Okay, so in total, 1,600 demonstrations. And we apply that schema to 2 new tasks, fill towel and unplug charger. And for each of the tasks, we have 4 data collectors and operating for 1 afternoon, and we can reach a success rate of around 80 to 90% of success rates. So those success rates are referring to executing the policy in novel environments on novel objects. Also the lightings, blah, blah, are also novel. Yeah, so I think this is pretty good. Kind of give you an estimate of how much effort you need to make in order for a policy to be okay-ish in a novel environment and novel object setting. But there is definitely a limitation in the sense that we didn't use any of the pre-training. Yeah.
Yeah, so I noticed that you have some pretty big standard deviations on these success rates, and I just wanted to know what that means for this experiment.
Yeah, so so actually because the success rate is, as I said, if you are, for example, grasping some object, it's very easy that you didn't end up grasping very stably, so that will count it as failure. So it is inherent, has a pretty large standard deviation for the success rate metric. And the standard deviation is, we did a kind of bootstrap estimation of the standard deviation of this success rate. So usually we'll prefer using the rubric as a score because it has much smaller standard deviation because it gives you the scores for each of the step. Yeah. Okay. So if you have the pre-training, hopefully you need much less data than this. And this is also single policy. If you train on multiple tasks that share some similarity with each other, you're also very likely to need much less data compared to 1,600. But this gives you the sense of how much data you need at most. Okay. Okay. So on the previous work, it's kind of like we know a method that could achieve around 80%-ish success rate, but we are not satisfied, right? If we want to use this thing for anything useful in practice, we need at least, for example, 99% of success rates. So how do we achieve that? As we have discussed, one way to do that is, for example, using reinforcement learning. But you will say, wait, RL is notoriously sample inefficient, right? You probably need a billion samples to train any policy in the simulator. But how could you make it possible to train reinforcement learning in the real world to improve the policy? So the last work I want to share with you is actually trying to resolve this issue. So this is what we call reinforcement learning with foundation priors. Okay, so let's talk about how human learns, right? So when I was small, and I don't want to go to the trash bin and put my trash into the bin. I want to throw my trash into the bin. And for example, you are trying to do that when as a small child. And how would you do it? So it is a very hard problem. So imagine if you're throwing a tissue paper ball into the trash. It's very hard because there are very complex aerodynamics correlated with the size of the ball, how tight you squeeze it, and the distance to the trash bin, of course. So what people did is actually we try a few times. For example, first we know what is the direction to throw, and then we try a few times, and we will notice that sometimes we throw too far, sometimes we throw too too close. And then we adjust our policies to adjust for the inaccuracy we observe in the physical world so that we can improve only within a few iterations so that we can do this super complex, hard to model task very well. And this is actually the intuition we take from human beings. That is, we have a lot of the knowledge about how to do the task, how to correct the task if we made an error, and also the fact that we know when we have succeeded. Okay, so those concepts actually maps to the Markov decision process very well, where the girl knowing I should throw in that way is a kind of a policy prior knowledge, right? You know roughly what you are doing, what you should be doing. And the fact that if I'm throwing too far, I need to go back a little bit, also map very nicely to the concept of value function, because you know, okay, the value of that is kind of bad, and I need to retract a little bit. And we also know the time we succeeded, and if we succeed, we remember the muscle memory and replay that muscle memory as accurately as possible in the future to accomplish that task. Okay, so so in this reinforcement learning with foundation prior work, what we did is we say the naive reinforcement learning is prior free. You just trial and errors. It's totally random trial and errors, and hopefully you can get some signal out of the random choices. But foundation priors, but reinforcement learning with foundation priors is a new paradigm that saying, okay, anything you have tried in the real world has to have some kind of prior knowledge, including the policy prior knowledge, the value prior knowledge, and the success 0 and 1 success signal. Okay, so how do we get those prior knowledge? Actually, for the policy function, you can just go through the bottom 2 levels of the pyramid. You will get 80% prior policy. And for the value function, we're using a previous work called value implicit pre-training from Jason Ma. So he did it when he was interning at Meta. So what this work is actually doing is looking at a bunch of human videos and trying to learn the human's optimal policies value function from those videos. And this is a value prior because it gives you an estimate of how much time do I need until I'm reaching my goal, assuming I'm a optimal policy, which is human, right? So yeah, so this is the value prior we're using, and for the final success reward, we're simply querying GPT-4. We didn't have GPT-5 at that time, but if you do the prompt carefully, the GPT-4 can actually give you a pretty stable 0 and 1 success detection. Okay, so how do we leverage those prior to learn? It's actually pretty straightforward. So what we did is for the policy prior, we use behavioral cloning laws to constrain on the policy function. And for the value prior, initially what we tried is we initialized the value function from those value priors, but we find if you fine-tune those policies, it has catastrophic forgetting issues. So what we end up doing is we find there is a paper from Andrew Ng back maybe 30 years ago that's called reward shaping, that you can form a shape reward by using this equation, which very nicely can guide the exploration of RL using the knowledge in those value function. And for the success reward, we just add it to the reward function. So the reward function has 2 terms. one of them being the shape reward and the other being the 0 and 1 success reward. Okay, and then we just run any of your favorite off-policy RL algorithm. In this case, we run a modified version of self-actor critic. Okay, so yeah, so those application of the prior knowledge is super straightforward. So, but I think the properties of those algorithms is really interesting. So the first one being, actually, you don't have to specify any manual rewards. You just go to those value priors and success reward priors, and they give you very dense reward and also give you pretty nice properties, as we will see in a short moment. And second is it will learn very efficiently. So from our experience, running those methods actually only takes 1 hour of time, can increase the success rate from like 20% to 85% on average. So let's look at one example. So what we did is we have an initial policy on the robot, which is doing some cattle watering flower tasks. So this is the robot. Okay, so you couldn't even pick up. And after we train for around 10 minutes, our robot can pick up the cattle, but not very stably. And after we train for 20 minutes in the real world, the robot is able to slowly pick up the cattle, but not able to finish the watering step. And after around 60 minutes of training, is able to grasp the cattle very stably and complete the watering step. So yeah, know that all of those learning happen in real world and happen without any manual rewards, just from the foundation priors. And actually the same methods works for many different tasks. So for example, here is pick and place, picking the eggplants and putting it into another place, opening drawer, opening the door, rotating the cap off the bottle, and even play mini golf on the table. So for all of those tasks, we use the same algorithm and no manual design reward at all. Okay. Okay. So yeah, so that's about the last work. Okay. And a little bit of final remarks. I think in the future we need a lot of work to improve for example, the pre-training, especially the reinforcement learning parts, because the work I showed today is has quite a lot of limitations. But I believe if we work along those paths, we can have a pretty general manipulation policy, not very far into the future. Okay, so yeah, there are definitely some open questions. For example, for the pre-training, as I said, how do we utilize the in the wild human videos? Now is only trained on robotic, manually collected human videos. And for the second stage, for the fine-tuning task, what about the data scaling in multitask? Does multitask has a better scaling because you can borrow different actions from the adjacent tasks? And for the RL, can we make it even more sample efficient? For example, reducing the now 1 hour to even a few minutes, because human doesn't need 1 hour to reinforce a skill. Human probably just needs a few minutes to be already very good at it. And also, can we transfer the high success rates across tasks? So the last work I showed is actually only training on each of the tasks one at a time. It doesn't transfer across different tasks. Okay, so that's it for my talk. So yeah, so I think now we can do a QA session. Yeah.
Yeah, so for
Thank you very much. Yeah.
It seems that the priors that you use are good enough for the task that you're doing. And let's say if you're doing a much harder task and your priors are not necessarily good enough to push that model to get into task. In that case, what do you do? Like, how are you going to train your priors? How are you going to train your robot calls?
Yeah, I think that's a good question. I think as a human, we should first think about for those hard tasks, do we expect any prior that will be good enough? If we expect that, we should go on and try to see how we can train the prior better, right? Should we use different type of algorithm to train the priors? And but if the answer is no, like for example, some tasks that human has never seen before, then probably we should relax on the sample complexity constraint. We should let the robots explore longer so they can complete the task. Yeah. Yeah.
I assume when you say video, you mean YouTube video, and do you see a near future where generated video can replace YouTube and you train on actually generated environment?
Yeah, I think, previously I would lean to a negative answer, but recently I see a lot of the OpenAI's Sora 2 work, and they're very good. And now I feel like I probably lean to yes. You can probably utilize those videos for the pre-training. Yeah. Yeah.
One question I have is regarding to the robot data and human data. When you present the very first part, I wanna know that is that only the video data, or does the data also contain motion controls and other trajectory stuff?
So are you referring in the first work? So in the first work, the video data only contains video information. It doesn't contain the...
Yeah, when you say robot data or human data, it's only video data, right? Or
Oh, so for the robot data, it contains videos and corresponding actions, corresponding robot actions for the robot data. Yeah.
for human data.
But for human data, it's pure video.
Okay.
Yeah.
Yeah. Thanks for the great talk. Really enjoyed it. Which of the three sections of the pyramid are you most excited to see future progress on, or which one do you think is the most important to focus on right now?
I think it's the pre-training part.
Okay.
Because so that is where most of the fruits come from, right? For large language model, you have very good pre-training, so you have a lot of even prompting a little bit can lead to very good behaviors. So I'm most excited about the pre-training parts. Yeah, I feel like if you didn't do the pre-training well enough, for example, the priors are not good enough, you are limited to what you can do. Yeah.
My intuition is that you still need to do the manual research for many of these tasks.
Yeah.
So I'm curious if you think it's more worthwhile for human effort to just do human in the loop dagger, where you kind of intervene to teleop it to help it rather than let it explore by itself and still need to be there.
Yeah.
Or do you think that won't be needed in the future? Or is there any advantage to real world RL over human in the loop dagger?
Yeah, so that's a very good question. Actually, we still need human recess in this case. But there is some work from Abhishek from University of Washington. What they did is they have, they basically treat resetting as another new task. So it's a multitask RL case. We didn't do that because that's too much effort. But I think human in the loop dagger is a very good way to do helping the robots. But I think the goal here is that in the end of the day, you couldn't having a human helping every robots. You want the robot to help itself. So, but I think human in the loop dagger is a pretty good intermediate form of improving the robot in practice. Yeah, and for this, for the third work to really being autonomously working in the real world, we have to deal with the multitask reinforcement learning. We have to deal with the safety constraints. Now the robot is also having some safe issues when you just let it go on itself. Yeah. Yeah. Yeah.
Connected question. Can you clarify, please, in this last example when you are training for 20, 40, 60 minutes, what is the definition of a tap or one round? Is it time bound or there's some detection that, okay, it's over, we're starting?
Yeah, so it's a time bound. So basically so it's pretty heuristic for the moment, but we basically set around 30 seconds time bound for each of the 12. But I think ideally the robot policy should output a done signal to indicate whether it thinks it has finished the task. But yeah, we haven't tried that in this project. Yeah.
So I remember that in the pre-training part, you said the successful rate was about 20%. So for the rest failure 80%, I'm wondering like how much of that is because you actually moved the robot to that position but failed to grasp or do that dedicated local manipulation there, and how much is because it just cannot reach that position?
Yeah, that's a very good question. Actually, most of the failure we observe is it can reach the maybe about 70% of the failure is it can reach the location but couldn't do the delicate maneuvers. And for the remaining 30%, we do see some like the rough direction is also could be wrong. But I feel like that's probably because we don't have a lot of data to pre-train on. And I bet if you have a lot of data, those type of errors will be very small.
So I feel like moving a robot is like an easier level of task here, but actually doing the grasping is another higher level of difficulty.
Yeah, it is. Yeah, it is.
So like generalization from the video data from human to robots sounds like it's a very difficult thing to do without any like if it would only take the video data without any like extra maybe pressure sensor on the fingertip or
Yeah, it is. I think the point of the pre-training is not making it towards 100%. I would say it's about for any of the motion you instructed, it vaguely knows, okay, that is the object I need to reach to, and that is the pose of my hand. I better try that pose. And it's totally fine that you have 0 success rate because you need to have the pose training. I think the goal there is not to have perfect success. Yeah.
I'm curious in your second paper.
Push success rate up to 88%. But then on repeated trials, there was this standard deviation, and there are mistakes being made on 15% of scenarios. Were there sort of consistencies in the failures? Like when you're observing the failures, it's you're finding that the robots making the same kind of mistakes each time, or I'm curious about those failures.
Yeah, actually, what we found, the failures are a lot of times very subtle. So for example, I don't have a mouse here, but if you imagine this is a mouse, and I want to pick up the mouse. So sometimes the gripper is only off by maybe 2 millimeters. And of course, the mouse is not a rectangular shape, it's some curvature on it. So it will just slip out of your hand. So I think a lot of those failures are really subtle, is really physics related errors. But we do see consistent type of errors within one policy, but different policies suffer from very different type of errors. Yeah.
Sorry, just a follow-up question on that.
do you think there's any meaningful way to actually use the data or videos of failure as well? So I know the model would already implicitly your some mistakes with application. But is there any more explicit way to
I guess the question is, how do we learn from the failure data? I think reinforcement learning is one way to learn from the failure data because it gives you negative reward. But I actually thought about this for quite a while, but I think the best thing you can utilize the failure data is to push away your policy from making those behaviors because knowing what is wrong doesn't necessarily tell you what is right. It just makes you to not able to make these wrong choices the next time. But what is the right choice? It doesn't necessarily tell you that. But I think the reinforcement learning already has the capability of using the data for that purpose already. Yeah. Yeah.
How close is the hardware to ripping and stuff to an actual human hand to grip and stuff? And then how much are the failures from that hardware difference than the other?
Yeah, so actually for the first work, we use a 6 degree of freedom hand. So it's pretty low degree of freedom. The 4 fingers only have 1 degree of freedom, so it can do under-actuated grip. And this thumb finger has 2 degree of freedoms, so it can do this 2 degree of freedoms. So we do find a lot of the errors arise from the mechanical parts of the hand because it's not able to even grip, like for example, a very thin object is not able to grip that. So yeah, that is also.
So is there an idea for human video data to somehow translate that into a better format for the specific hardware?
Oh yeah, actually we already done that. So there is a retargeting phase. There is a retargeting phase that we retarget the human hand to the robot morphology. Yeah, we already done that. Oh yeah.
One more question. So if you scale with the pre-training, do you think that the scaling laws for imitation will be very different in terms of what diversity is needed, or do you think it'll be very similar?
I think it totally depends on the data distribution. I think it will be the same, but the slope of the scaling law might be very different because if you scale the pre-training data, you have no choice of the data diversity except for what data sets you are using. But even that, you have some natural diversity within a single data set, so they will still climb up the scaling law, but probably in a much lower rates compared to the manual data collection. Okay, seems like we have all the questions answered. Yeah, thanks everyone.